never land very quickly. So you always have understanding first, and that's what I try to do in my presentations, to give understanding. In fact, I don't think I put an equation in a presentation for probably 10, 15 years now. Very rare that I'll do that. I try to give understanding. Leave the equations for the textbook, leave the equations for the paper that gets published. That's where you can sit down and look at things and carefully understand them. But electromagnetics, I'll give a brief a description of how method of moments works. I was a student of Roger Harrington, who developed method of moments, and I spent probably about 3 years learning the method of moments. Here, you're going to learn method of moments in about 5 minutes. Basically, the way we apply method of moments in general is a way of converting any linear, has to be linear integral differential equation into an array of equations, simultaneous equations, a linear simultaneous equations that can be solved with a matrix inversion. It doesn't have to be restricted to electromagnetics. It doesn't have to be restricted to planar circuits. But it does have to be linear. Now, the way method of moments works for planar circuits is you take a planar circuit and you divide up just the metal of the circuit. Not the volume, just the metal of the circuit itself into small, say, rectangular subsections. This is true for all planar electromagnetic method of moments tools. Well, it doesn't have to be. Okay, so you got a bunch of little subsections. Now you take just one of those subsections. Just take one of them. Throw all the others away. Now, one of these subsections, you got layers of dielectric and stuff. Now you calculate you put a gob of current onto the subsection. What the exact shape of this piece of current is doesn't matter too much right now. It matters when you get into the equations. We'll just say there's a bunch of current on this one subsection. There's a bunch of current. Now that current, you got a little current flowing there, a little patch of current flowing. That current generates electric and magnetic fields everywhere. So what we do is we calculate what the electric fields are, tangential electric fields in particular. Calculate what the electric fields are everywhere due to this little piece of current. And now we do this for each subsection, one subsection at a time. When we're all done doing that for each subsection, one subsection at a time, we put current on all the subsections simultaneously. Current on all this, then we adjust the current on all these subsections such that the total voltage is zero. We can't have voltage across the conductor. The total electric field is zero. Everywhere where there's conductor, we can't have voltage across the conductor. The currents that give us zero voltage everywhere is the current distribution on the circuit. Once you have the current distribution, things like Y parameters, Z parameters, and S parameters follow immediately. So the key is, once you have a patch of current, is to calculate the voltage it generates, or a tangential electric field, it generates everywhere. And then you adjust, you put current on all the subsections simultaneously and adjust the currents so that you get zero tangential field everywhere where there's conductor. The currents that do that are the current distribution, and that solves the problem. Now, that's a conceptual description. Get a little bit more mathematical here, still without using any equations. What you do when you have current on one subsection and you calculate the voltage on another subsection, you're calculating the coupling between two subsections. Current here generates voltage there. We have to know how much current, if a certain amount of current here generates a certain amount of voltage there, so that when we get current on all the subsections, we can adjust the currents so that the total voltage goes to zero anywhere where there's a conductor. And that fills up a big matrix. You've got 10 subsections. You've got 100 couplings to calculate. You know, subsection 1 generates voltage on subsection 1. That's important. Subsection 1 generates voltage on subsection 2. That's the second element in the matrix. Subsection 1 generates voltage on subsection 3, and so on. So we fill up the matrix with current generating voltage. Current equals big matrix times voltage. Well, there's an equation, but it's just a hand-waving equation. And you invert the matrix. When you invert the matrix, you're solving for the current everywhere, given 0 voltage on every subsection. Now, there's one problem with that description yet. Some of you may have caught it. If we've got 0 voltage everywhere, that means 0 current, right? Trivial solution. 0 voltage, 0 current, yeah, problem solved. Of course, you get the 0 is what you get on a test, too, if you put down that answer. What we have to do is we have to pick one subsection that will be, we call it a port subsection. This is where the excitation goes. We put 1 volt on the port subsection, and that generates current on the other subsection, and we adjust those currents to get 0 voltage everywhere except on the port subsection. So that's an excitation. That's essentially, if you look at it mathematically, when we invert this matrix, we're taking 1 row or 1 column of this matrix, and we put voltage on 1 subsection. And the input impedance that you see for that, if you have current on this subsection, you can calculate the voltage. You say 1 volt across it, and it's got 2 amps. 1 volt and 2 amps, that's half an ohm. Input impedance is half an ohm. You know the voltage, you know the current. So now you can solve, it's essentially Y parameters. And that's how we get the Y parameters. We calculate in Sonnet, in our electromagnetic software, we calculate the Y parameters. We don't calculate S parameters. You try to, some of the softwares out there will solve for the current, and then you see a standing wave. And you try to figure out what the standing wave is, what the phase is, and the magnitude, etc. And that can be a little complicated. It introduces error. It's a big problem if you start having loss. It's a big problem if you don't know what the line voltage is. If you have strip line with uniform dielectric everywhere, you can calculate the voltage easily just by doing the line interval. If you have microstrip, you have different dielectrics, voltage is no longer unique. So by calculating things like Y parameters based on current and voltage only, don't worry about standing waves. We calculate the Y parameters, and the voltage is just the voltage on the subsection, and the current is just the current flowing through it. There's no ambiguity. We calculate the Y parameters essentially exactly. And then if you want S parameters, we convert to S parameters. We don't have to actually figure out what instant reflected waves are. And that's very powerful. There's quite a few people out there that haven't figured that out yet. But we've been doing this for 22 years now, and it works really well. Getting essentially, you can get asymptotically exact answers in this matter. In fact, that's kind of unique about electromagnetics. If you look at any other field of numerical physics, like computational fluid dynamics, thermodynamics, stress and strains in solids, none of these fields can you get essentially exact answers or asymptotically exact answer. Take the meshing down finer and finer and you get a more accurate answer. You cannot get asymptotically answers in any of these fields except electromagnetics. You always have things like turbulence, for example, in computational fluid dynamics. You put an ideal solution for an example, a flag blowing in the wind, it flaps. You can't get that out of a normal computational fluid dynamics. Turbulence. You can figure out where it's going to happen, but you can't figure out exactly what the turbulence is going to do. In electromagnetics, until you get down to the point where you're counting individual photons, you can get essentially exact answers, asymptotically exact. As you cut the cell size in half, for example, in meshing, you cut the error in half, typically. And you can extrapolate down to essentially exact answers. That's a really beautiful part of electromagnetics, is you can get arbitrarily precise answers. A lot of microwave engineers are throwing that away, not realizing you can get exact answers. And that's because some of the softwares out there don't give exact answers. They aren't asymptotically exact. That's something we've taken very, very great care in to make sure is that we don't make any approximations that throw away the asymptotic exactness. And that's helped us in a number of cases. For example, in silicon RFIC design, spiral inductor Q. We had a situation here a few weeks ago, several months ago, IBM Fishskill, where measured Q was like this, and calculated Q was up here. And two other electromagnetic programs were saying the same as the measured Q. We found out, because we knew our software was asymptotically exact, we evaluated cell size, we evaluated metal thickness, we evaluated box sizes, error sources. And none of those could explain, in fact, how Q was higher. We finally started looking at the measurement. There was a problem with the measurement. There was a measurement error, which turns out to be quite common. In fact, that will be published in the December issue of this magazine, IEEE Microwave Magazine, what the measurement error is. If you work in silicon RFIC, strongly recommend you look at it. I can email you a pre-release copy, pre-publication copy of it if you want as well. One thing I forgot to mention during the Maxwell presentation, if you want to go into Maxwell legacy more, the electromagnetic legacy in more detail, I published an article in the June IEEE Microwave Magazine. You can download a PDF from IEEE Explorer, get it from Professor Zhu, or from myself. I'll be glad to email it to you. Okay, so things are, in microwaves, it can be asymptotically exact. Now, if you want to get down into extreme situations, Maxwell's equations fail. Actually, let me talk about one other thing for a moment. I was sitting next to someone at a conference about 2 years ago, maybe 3 years ago now, and the person found out I was, worked for Sonnet. Don't think he realized I was the founder of Sonnet, but he found out I worked for Sonnet, and he kind of sneered at me. He was using somebody else's tool. Kind of sneered at me. He said, "I bet you think Sonnet gives the right answer and all the others give the wrong answer." And I said, "Well, all the other tools give the wrong answer, but I will 100% total absolutely guarantee you Sonnet gives the wrong answer too." That's what I said. Sonnet is guaranteed to give you the wrong answer. And that's true. The question is, how wrong is it? All the software, all numerical calculators give a wrong answer. The question is, how much wrong is it? What is the error? In publications, we will frequently publish we call it good agreement between measured and calculated. In fact, I see that so often we have come up with our own acronym for it. GABMAC, G-A-B-M-A-C. Good agreement between measured and calculated. GABMAC. And it's nice to see that. It gives you a warm, fuzzy feeling, but that's not what we're after. We're engineers. We're interested in things that go wrong. And we want to know what the error is. You have two curves like this. I've seen two curves like this, and they're described as giving good agreement between measured and calculated. And everything gets good agreement between measured and calculated. We're not interested in that. We don't want to see that. What we want to know is the measured and calculated are different by X%. We want to know what the error is. And don't ever make an error by publishing. It's an error to make to say my analysis gives 1% accuracy. No, I don't think it, unless it's a terrible analysis. Your analysis does not give 1% accuracy. It gives 99% accuracy and 1% error. Oh, don't get error and accuracy mixed up. Error is what's wrong, and that's the 1%. We want error small and accuracy large. So always keep that in mind. And when publishing papers, it's important to do an error analysis to find out what the difference is, and if possible, to find out what the cause is of the errors. Our finding out what the cause of the error was in that spiral inductor Q measurement from IBM Fishkill. I actually sat down for 2 weeks on that one to figure out that. It was because of we had understanding. We were convinced Sonnet gives the wrong answer. The question is, how much wrong does it give? And we had an understanding how much wrong it gives. You find out what the error due to cell size is, you cut the cell size in half and see how much it changes. That's about half the error. Cut the cell size in half again. It changes by half as much. That's about half the error. So we had a good handle on how much the error was. And because we understood that, we knew the error. We evaluated all the error sources in the Sonnet. None of the error sources could explain the problem. So that's why we went to the measurement. And that took about 2 weeks of intense work. What I like to do is I did that personally myself with the assistance of another employee at Sonnet. I like to immerse myself in problems. I don't do this real often, but I do it every now and then. And it was total immersion. I worked on nothing but eat, sleep, and the problem for 2 weeks. It wasn't until we were into a problem a week and a half that we decided to start looking at the measurement. And that's, took very, very intense. But the only reason I was able to do that is because we have good understanding of the error sources. Now, if you go working with an electromagnetic analysis, assuming it gives you the right answer, and you're not critical about how much the error is, you're going to see a difference between measured and calculated, and you'll call it GABMAC. It's good agreement between measured and calculated, even though there's differences there. And then you won't worry about thinking of any further. So it's very important to understand the error sources. Rather than hoping your analysis, whatever field you're in fact, rather than hoping the analysis gives the right answer, assume it's the wrong answer, because it is the wrong answer. And then figure out how much it's wrong, and what are the error sources, and quantify them. That's very important. Now let's drop back a little bit and talk about where electromagnetics goes wrong. All theories in physics fail. Matter of fact, that's the way physics works. Is people will propose a theory, and then immediately everyone will try to start breaking it. And it is a given that every theory will break. For example, theory of relativity. How many people believe theory of relativity is true? One, you know the answer I'm looking for is it's not true. Okay. How many people are convinced the theory of relativity is wrong? Okay, that's the right question to ask. Okay, nobody's convinced it's wrong. Actually, if you ask a physicist that question, he will tell you absolutely theory of relativity is wrong. It has a glaring deficiency. It's a field theory. What is the gravitational attraction between Earth and Sun? No problem. Relativity does that fine. What is the path of starlight? The starlight goes past the Sun, and how is it deflected by the gravity of the Sun? No problem. Got that down to the nth degree. Now, in a hydrogen atom, what is the gravitational attraction between a proton and an electron? It's dominated by electromagnetic forces, silly. Well, okay. Well, let's calculate it. Well, according to gravitational theory and the theory of relativity, gravitational attraction is about 10 to the 20th less than the electromagnetic forces. 10 to the 20th is a that's a huge difference. Never measure it. Not possibly important. Okay, it is important in the first few milliseconds of the history of the universe, though. Now, if you get gravitational attraction between atomic particles that are that small and that close in the first few milliseconds of the universe, it could be very substantial. But it's guaranteed relativity isn't going to predict it, because now you need a quantum theory of gravitational. Relativity is a field theory. It's not a quantum theory. There's no quantum theory of gravitation yet. We can't measure stuff back then. Gravitational force between an electron and a proton, we can't measure today because they're too far apart. So all theories in physics are guaranteed to be wrong. Maxwell's theory is just where and when and how they're wrong. And when you find out they're wrong, that's when you get to get the research grants to figure out a new theory that applies for that case. And then when you figure out the new theory applies for that case, you go around trying to break that, find out where it breaks. It's guaranteed to break it sometime. Quantum electrodynamics, I don't think has been found to be broken yet. People are aggressively looking to try to break quantum electrodynamics. Quantum electrodynamics picks up where Maxwell's theory fails. Maxwell's theory fails for, as I mentioned during the Maxwell lecture, for low power when you count individual photons. And let me give you an example. It comes out of that book by Feynman, Richard Feynman, QED, The Strange Theory of Matter and Light. I myself have never taken any coursework in quantum electrodynamics, but the book, the Feynman book, describes some beautifully simple terms. So someone of any kind of even marginal engineering knowledge will be able to understand it beautifully. You all remember the double slit experiment. You have two slits. Let's pretend my fingers are the slits. You have two slits. You shine coherent light on the two slits, laser light perhaps. And on the other side, you see a beautiful interference pattern. You don't see just two blobs of, you don't see the blob of light. You see a beautiful interference pattern with nulls and such, depending on the separation of the slit in terms of wavelengths. Okay. Now for quantum electrodynamics, let's reduce the power. Maxwell's theory works beautifully for that. It works perfectly. Let's reduce the power. We'll reduce the power down and down and down until there's only one photon at a time coming out. Okay, if there's one photon at a time coming out and going through the slits, you can't split a photon in two, make two photons. You can't do that. It's just one photon, its energy is set, and that's that. So a photon comes towards the two slits. There's some randomness here. Which slit does it go through? It has to go through one or the other, right? Well, it goes through one. It can't go through both. It goes through one slit. Then there's going to be no interference pattern. right? Because there's nothing for it to interfere with from the other slit until the other photon comes, the photon later time comes along and goes through the other slit. Can't be any interference pattern. Okay, you can actually do that experiment. You do the experiment and just let it run for a long time. You record where each photon lands, and you add up the photons, and pretty soon there's an interference pattern appearing. Even though only one photon at a time comes, and it goes through only one slit at a time, you get this interference pattern. Wow, how can that be? Maybe quantum theory is wrong. Maybe the photon actually goes through both slits at the same time. Okay, we can actually put a little detector on one slit or the other or both and detect which slit the photon goes through. Okay, so you run the experiment. You're detecting, okay, it never goes through both slits at the same time. It's always going through one slit or the other. And we detect it, and we let the experiment run, and we don't see any photons going through both slits. It always goes through one slit. And then we look over here at the pattern that all the photons have made. The interference pattern has disappeared. Haven't changed anything about the experiment other than detecting which slit the photon goes through. When we know which slit it goes through, the interference pattern disappears. How can nature know that? It's actually related to the Heisenberg uncertainty principle. In fact, if you make the detector so that you have a certain probability of detecting which photon it goes through, so let's say you've got a 50% detection probability means you know nothing. You just took a random guess. So let's say 75% detection probability. So you're halfway. You've got like half uncertainty. When you look at the pattern, it's half interference and half non-interference. Nature knows what's going on here. What it amounts to is if you don't detect the photons, there's no photon-electron interactions. It goes through the slit. The photon, in quantum electrodynamics, they model it as taking every possible path. In this case, there's 2 paths. Let's say there's 1,000 paths, 1,000,000 paths. It takes every single possible path. And then it's a complex probability that adds up. Remember how I said back in the lecture, Maxwell lecture, you have to take the square of an electric field to get something you can feel? Like energy density? You can't feel the electric field directly. The Schrodinger's wave functions, they're the square root of a probability. You have to square them and you get a probability. So you take all these Schrodinger wave functions, all these photons, you add up all the complex probabilities. It isn't even a real probability, it's a complex probability. You add up all the complex probabilities of the photon taking every single path, and then you get the interference pattern with one photon at a time going. As long as you don't know, as long as you don't measure where that photon is, it will take, every single path. If you know which path it's taken, then all the other paths are eliminated. And your interference pattern goes away. Quantum is a really, really weird universe. It just does not correspond to practicality. And Feynman, in his book on QED, The Strange Theory of Matter and Light, he emphasizes very strongly in the beginning of the book that we being the physicists, do not understand why quantum electrodynamics works. The same thing with electromagnetics. We don't understand why it works. But what we do know is that when we use these strange square root of probability complex functions, the wave functions, and go through the little routines with them that have empirically developed over the years, that we get calculations very, very accurately. In fact, with quantum electrodynamics, by using different electron-photon interactions, add up a huge, long probability, you can actually calculate the magnetic moment of an electron. And it's a huge calculation to calculate it out precisely. Lots of probability. It has to be done essentially by hand. You can't program up a computer to do it. But they have calculated and measured the magnetic moment of an electron to an accuracy that corresponds to measuring the distance between New York and Los Angeles to plus or minus the width of a human hair. And the calculation and the measurement come out to be the same, almost exactly the same number. And that was the status of a few years ago when Feynman wrote his book. I don't know what the status is today. Any physicists here who know the status of that? Okay. But that's a quick summary of some of the topics covered in that book. It's, QED is a strange world. And coming back to electricity and magnetism being abstract quantities that we cannot perceive, another way to look at that, electric and magnetic fields that we cannot perceive directly. Another way to look at it is you could easily write in a, well, let's say average family has 2.3 children. That's an abstract number, 2.3 children. I cannot imagine 2.3 children, unless you want to get really gross. I cannot imagine 2.3 children. But you can easily write an electromagnetic field, the equations for an electromagnetic field, electricity and magnetism, that corresponds to the energy of 2.3 photons. We can't have 2.3 photons, but it's allowed by Maxwell's theory. So not only are Maxwell's electric and magnetic fields abstract, we cannot perceive them, they are impossible with unity probability. You have to have an energy of exactly an even number or an integer number of photons to have a field that could even exist energy-wise. And then you don't get the complex probabilities interactions. The double slit experiment won't work with Maxwell's equations. When you get down to individual photons, can't predict what's going to happen there. Maxwell's equations predict, that you'd have no interference, but the interference really happens. So, and it doesn't matter whether it's 2.3 photons or 2 billion 0.3 photons. Such a field can't exist. However, the saving grace here is, and this is what I've been, running my business on for the last 22 years, is that for practical microwave applications, as I was discussing in the beginning of the lecture, for practical applications, we're not talking about the case where you count individual photons. But for practical applications, Maxwell's equations are essentially exact. We can treat, for our work, we can treat them as exact. We can pretend electric and magnetic fields are real. We can, for whatever you folks can measure here, or in 100 other universities around the world, or 1,000 other companies around the world, whatever you can measure on your network analyzer, whatever you can build, we can analyze essentially exactly. As long as you don't have to get down to the point where you're counting individual photons, Maxwell's equations work fantastic. And it's a very beautiful theory. Every time I go over Maxwell's equations, I see something new. And it's the theory, as I mentioned, that opened up the entire 20th century physics. It was, abandoning of Newton and F equals ma, and then allowing relativity to be developed, quantum theory to develop. All these are field theories, or quantum theory. And no F equals ma, no Isaac Newton. Those things are allowed to happen because of Maxwell's field theory. And one thing I'll mention as well, Feynman, Freeman Dyson, in the essay that I can email to you if you like, complained that because Maxwell is very modest, his electromagnetic theory was not adopted for 20 years until Hertz did his work with experimental validation. It was not adopted for 20 years. So Maxwell, because Maxwell is modest, set back the field 20 years. And that was a very terrible thing to do. He should have been a self-promoter like Newton was, promoted his electromagnetic theory. And then if people had sat down and taken notice because Maxwell was promoting it, then validation would have come 20 years earlier, quantum theory would have come 20 years earlier, relativity would have come 20 years earlier, E equals mc squared would have been 20 years earlier, nuclear energy and nuclear weapons would have been 20 years earlier. World War II would have been at the same time. Might have had a totally different outcome. So, if I ever had a chance to talk to Freeman Dyson, I'll mention that and say, maybe it's just as well Maxwell was modest. And he set back the field of physics 20 years. Physics needed setting back 20 years in light of subsequent events. One thing I've mentioned during the presentation, and I think is it's quite important, is the really wonderful, the really genius things, the amazing things that happen in physics are simple. The simplicity of genius, the simplicity of Cousin Jemima's paintings of Maxwell, the simplicity of Maxwell's idea for color perception, quantifying color perception, determining it's a simple idea. Feynman is a beautiful example of simplicity. You take the most complicated things and make it sound simple, like quantum electrodynamics. If you read his book, you'll see firsthand the genius of simplicity. But it's the simplicity that can handle difficult problems, make difficult problems appear to be easy to solve. It's just a matter of looking at things a little differently. Don't be afraid to look at things differently. You might come up with some solutions. Back, when Maxwell first went to high school and he got beat up by his classmates, it's because at that age then and now, kids of that age, I think particularly boys of that age, tend to want things to be uniform. And anybody that's different, gets hassled. And it's important to abandon that, because if you're willing to be a little different, you can come up with some brilliant things. If you're being a little different and it doesn't work, doesn't achieve something that you want, forget it. Be different in a different way. Be different in a way that's useful, that turns out to be useful. And it's okay to make some mistakes now and then, and then you come back. But this kind of an example of that, one thing you can do, for example, give a problem of ripping a telephone book in half. And that's what I'm going to do right now. And normally you think ripping a phone book in half is difficult to do, but it is pretty hard to do. But if you think about the problem a little differently, you can come up with different answers that sometimes might be easier. For example, I'm trying to rip it this way. It doesn't want to go. Okay, I'll rip it this way. It's still not going. I think what I need here is I think I need everyone. We can establish kind of a mental field here. Maxwell had his magnetic fields that you can't see, we can't perceive. We'll have a mental field here. We can't see it or perceive it, but we can all. I want everybody's support here. I want you to look at this phone book and visualize the phone book ripping. And we should be able to come up with a nice, simple, easy way to get this ripped phone book. Is there anybody here who thinks I can't do this? Is there any doubt? Is everybody convinced I can do this? Anybody doubt that I can do this? Anybody at all? Okay, one person. If nobody said they doubted that I could do it, then I wouldn't do it, because why should I do it if you're all convinced that I can do it? But we've got one doubter, so put aside your doubt for just a moment and become convinced that I can do it. I need everyone here visualizing the phone book ripping in half. And what we need, we need the genius of a simple solution here. And okay, visualize it ripping in half, and the genius of a simple solution. This is not my solution. I saw this. This is another simple solution. If you look at things differently, whatever problems you're coming up with, look at things differently. And like Feynman, like Maxwell, and like many others throughout history, if you look at things differently, whatever field you're in, sometimes you come up with solutions that don't work. Sometimes you come up with something that's really fantastic. Just be willing to look at things differently. Look at things differently, and you come up with a good solution. Thank you for your attention.